Hi everyone, welcome to another video in our series. We are continuing on with the things we know about parabolas, quadratics, things like that, and we're going to apply everything that we've learned so far to solving some worded problems and some application questions of parabolas here. Now, I'm just going to work through this one example really slowly, reinforcing the ideas we have learnt so far and how we can apply them to the certain context of a question. Now, here we have a measuring question. We have a piece of wire measuring 100 centimeters in length is bent into the shape of a rectangle, and let X centimeters be the breadth of the rectangle. Now, with any question like this, any worded question, we want to first start by drawing a picture. Now, we have some kind of wire here that is 100 centimeters in length, and we're going to bend this to form the shape of a rectangle. So instead of having something like this, we're going to have a rectangular shape. Now this 100 centimeters, that is just the length around of which we bent the wire to form this shape. So looking at this shape, this is going to be the perimeter of my rectangle. So my perimeter equals to 100 centimeters. And we're going to let X here be the breadth. Now, this is a rectangle, so these two sides are equal and these two sides are equal. Okay, now we want to use, in part A, use the perimeter to write an expression for the length of the rectangle in terms of X. Now, when we're dealing with rectangles, we know that this length plus this length, or two lots of this length L, being added to these two lengths of X, in other words 2X, is going to equal my perimeter, my total outside length here. So we're going to set up an equation here. So we know that two lots of my length plus two lots of my breadth X equal to 100. So now we want an expression for the length L. And to do that, we want to isolate the L. So we want to get everything on the other side, leaving L on its own. And we get that by just solving this equation. So I'm subtracting 2X from both sides. That gives me 0 here. And leaving me with 2L. And that equals to 100 minus 2X. And we can divide both sides by 2 to get us the L. So I get that my length L equals to 100 minus 2X all over 2. And now I can see there's a common factor in the bottom denominator and the numerator. The number 2 goes into both the numerator and the denominator. So if I pull out a factor of 2 here, I'm going to get left in my brackets 50 minus X all over 2. And these two cancel out to give me an expression of L as 50 minus X. Okay, that's part A. We have just found an expression for the length here, the length of the rectangle. Now for part B, we want to write an equation for the area of the rectangle, A centimeters squared, in terms of X. So here, down the bottom, we expressed my length in terms of X. And our area, this space inside, is given by my length multiplied by my X. My length multiplied by my breadth. So what we're going to do for part B, we have that area equals length times breadth. And I have an expression of 50 minus X as my length, and I have a breadth of X here. So that is my expression for my area. And let's just write this a little nicer. X outside of 50 minus x. That is my expression for my area. Now, continuing on with this, and I promise we're going to actually apply the things we've learned from quadratics and parabolas here, but you can hopefully already see that if I expand this expression here, I'm going to get some kind of x squared, some kind of quadratic, because these two x's are multiplying by one another. Now for part C, we want to decide on suitable values for x. Now, here is where context is important. We want to decide on what's going to be, because this is a measurement question, what values can x, for example, take on? So, using what we have here, this is a measurement question. Now, since this is a measurement question and x is some length, the length can't be negative. So my length of x has to be greater, my breadth of x has to be greater than 0. So this guy here has to be greater than 0. But now also my length here, 50 minus x, that also needs to be greater than 0, because I can't have a negative length. So I also want to write that not only is my breadth going to be greater than 0, my length, 50 minus x, is also greater than 0. So we want to just fix up this inequality, because we have this inequality on the right here that we need to solve. So let's add x to both sides here to get x on its own. And this gives me that 50 is greater than x, or x is less than 50. Okay, so this is just all about, and a lot of these questions, particularly with measurement, it's all about context. We have to remember that at the end of the day, we are looking at measurements. And because from what we know about length, lengths can't be negative, so both this and this need to be positive, need to be greater than 0. So therefore, this is going to give me an inequality for the values that x can take. So x has to be greater than 0, and it has to be less than 50. So this is what we mean by the suitable values of x. Okay, now we're slowly getting there. We want to, in the next part, this is where we are going to start applying what we know about parabolas here. Now, we want to sketch a graph of A, the area, so the area being my vertical, versus X being my horizontal. Now, anytime we say a graph of, for example here, it's a graph of A versus X. We are looking at the A, or whatever this first term is, as my Y graph. As my axis of my graph. Okay, so we have this here, and what values of X can my parabola take up? Well, anything greater than 0. So we're going to use this open inequality symbol to show that it's greater than 0 but not including 0. And then an open one here as well at 50. So I have 0 and 50 here. And I want to sketch this graph. So let's go back to my expression for my area up here. My area equals to equals to x outside of 50 minus x. I want to think about how I can sketch this thing here. Now, I can expand this as well. So this is like saying 50x minus x squared when I go through and actually expand. So when my outside term multiplies with both my inside terms. So I can write this as a equals 50x minus x squared, or in the general form of our quadratic equations, I'm going to do my x squared first. Now this is a negative parabola, or there's a negative in front of my x squared, so that means my parabola is going to be concave down. So it's going to look something like this here. So that's already giving us a bit of a hint. So we're sketching this for all the suitable values of x, of x here. So in between these 2 points here. And now if I want to draw this, I already have my intercepts, even though they can't be exactly these points. And I can also find my y-intercept or my a-intercept by substituting in 0 for the x, because I get an intercept on my y-axis or my a-axis when my x is 0. So popping this here, 0 multiplied by whatever this is going to give me 0. So there is an intercept here. And just to draw this, what else do we know? Well, we know there's going to be some kind of maximum turning point on my concave down parabola. And I want to find that here. Now, using what I know about the turning point, I know that my turning point, I can get the x value when I do minus b, the coefficient of x, over 2a, where a is the coefficient of x squared. So substituting these values in, I get minus 50 over 2 times minus 1 here. 2 times minus 1. In other words, that gives me negative 50 over negative 2. These two negatives are going to cancel out, giving me 25. So I have a maximum turning point at x being 25. And I can find my y-coordinate, or my a-coordinate in this case, by just substituting. So we'll write here, can find a coordinate by subbing x equals 25 into the equation. So my area A is going to be 25 outside of 50 minus 25. Or in other words, 25 multiplied by 25. And that gives me 625 here. So that is a really big y-coordinate or a-coordinate of my, that's in a different color, sorry. That's going to be my a-coordinate here. So my parabola that is modeling this particular measurement is going to look something, whoa, that's not good. Something like that. So we have sketched the graph of A versus X for the suitable values of A. And now, in doing this, we've kind of already answered the next part of the question. Our next part is to use the graph to to determine the max area of the max area that can be formed. Be formed. Okay, so we've already done that. We saw that the maximum turning point happens at the length of x, at the breadth of x centimeters, and an area of, that makes an area of 625 centimeters squared. So that's my area. So therefore, just reading off the graph that we've done, the max area equals 625 centimeters squared. And finally, in part F, we want to find what will be the dimensions of the rectangle to achieve this maximum area. Okay, so we had the dimension of x being 25 centimeters. We already knew that. And the length, L, is going to be 50 minus x. So we're kind of double handling. We're sort of doing what we have already done in order to draw this graph, but we get 50 minus substituting in this value of x into my expression for my length. That gives me 50 minus 25, and that gives me 25 centimeters. So these are the two dimensions, x and L, that give us the maximum area. And what gave us that maximum area was modeling this scenario using what we know about quadratics and parabolas, and sketching a parabola and understanding that parabolas, or anything that models a parabola, can have either a max turning point or sometimes a minimum turning point. But since we're trying to find the maximum area that can be formed, we are using the fact that this is a concave down parabola, which has a maximum turning point. But that brings us to the end of the video. Thank you so much for joining me, and I will see you in the next one.